Thank you for having me. We stay in the realm of fault attacks, but now we look at defense. Shortly about me, I'm Jonas. I'm a PhD student at the Technical University of Graz, and I focus on hardware fault attacks from software, so no hardware to attack involved, microarchitectural security, side channels, and also a bit on energy efficient computing and security. Who have you heard of Rowhammer before? Perfect. Because it's out since 2014, so we almost have 10 years with Rowhammer. Many attacks were shown, many mitigations were proposed, but now, 9 years later, almost 10 years, it's still unsolved. And this is a big problem, of course. Most of you heard of Rowhammer. I will still give a short introduction what it is. On the left, you can see the Rowhammer code that does the hammering. On the right, you can see the DRAM, or schematic of it. The hexagons are the cells that store every individual bit. And now this aggressor code accesses rows in the DRAM. It then has to flush them from the cache, and it accesses them again. And if attacker code does this very quickly, bits start to flip in some of the cells. And the nice for an attacker, is that these are special and vulnerable cells, so the bits can flip everywhere. If I once found faulty bits, these bits probably will fault again when I attack it. And yes, this is how this looks like on a real machine. This was a live demo we presented last year at Black Hat in London. And this is an off-the-shelf Chromebook device running an ARM CPU with LPDDR4X memory. This is memory with on-chip ACC and an Rowhammer mitigation in the DRAM. So this should be a fully protected device. It takes some time. It tries different rows, and I think now the first flips should show up. Now, next one. Here they are. Here it found 2 flips, and it continues hammering. And more flips are coming in. And all of these flips are can potentially break the system or privileges. So what can we do with that? We can do privilege escalation. We can escape browser sandboxes. Actually, these are the first 2 exploits that were shown by Google researchers in 2015. We can also escape browsers from JavaScript. We can escape virtual machines. Attacks are possible over the network. There was also an attack shown that can read memory and read cryptographic keys. And there is also more interesting stuff, like, for example, changing kernel code to make it a Spectre gadget. So Rowhammer can do a lot of stuff, and this is bad because DRAM is pretty much everywhere. So, of course, many mitigations were proposed. There is ECC and chip kill. ECC is common in every server out there. There were proposals to detect Rowhammer attacks in software, for example, through performance counters, because we see a lot of cache misses when running a Rowhammer attack. There were proposals to do physical isolation, so don't put kernel code and user code, for example, next to each other in the DRAM, so in neighboring rows. The most active mitigation right now is TRR, and it adds additional refreshes to attacked rows. And then there were other proposals to improve the physical cell layout, so in silicon, to design the whole DRAM. But this adds more space and therefore is more expensive, and no one wants expensive DRAM. So most of these mitigations focus on characteristics of Rowhammer. For example, that it's infrequent. If it's infrequent, ECC or chip kill is enough. Or that we can detect it through performance counters, or that physical isolation is good, or these additional refreshes of neighboring rows, because Rowhammer only works on distance 1, so on direct neighbors. But the problem is that these characteristics are incomplete. And this is why we still have this cat and mouse game where new mitigation is proposed, and then a year later a new attack comes out. Because we don't really understand the problem, and maybe the best example we presented 2 years ago already now is half-double Rowhammer, where this is what we saw in the video before, actually, where we have modern DRAM with TRR, with this mitigation. And now we don't hammer direct, at the direct neighboring distance, but one further out. So we hammer these rows, and after some time, this TRR mitigation kicks in, and it refreshes the neighboring rows of our attack rows. But for reasons we don't fully understand, the DRAM vendors maybe know, but we don't, this actually flips bit in here. So here we don't only evade the mitigation actually helps us hammering. So this is of course bad. So we can now hammer over distance too, so also evade other mitigations that try to do physical isolation or stuff like that. So we have to rethink Rowhammer mitigations. We need a generic approach to data integrity protection that doesn't focus at all on where the bit flips are coming from. Because this Rowhammer problem is so complex, and there could even be other problems out there, or there are also cosmic rays and stuff. We don't care where the bit flips are coming from. If there are any bit flips in the DRAM, we can detect them and we can protect them. We still call it CSI Rowhammer though, because it sounds cool. So Rowhammer is in the name there. And I will now introduce shortly how this works. So here we have the DRAM. This is where Rowhammer happens. And here we see the CPU with the memory controller. The memory controller is the thing that talks with the DRAM. And now on every read and write, it computes a message authentication code. That's like a hash, but with an additional key of the data. And when it's write data, it puts this MAC and some parity bits on an additional chip on the DRAM. So this is just normal ECC, a normal ECC DRAM. And then on every read, it compares the MACs, and we know if the data integrity is correct or if it's not anymore. So it is pretty simple data integrity protection. If they're not correct, we can correct a single bit flip in hardware directly to be extremely quick. And then we delegate for more bit flips the work to the operating system. With a new exception, we introduce that is handled by the operating system and then does two things. Either correction as a search, which basically is brute force, I will talk about later, because it's not that bad. And then advanced correction, where we can do pretty cool things because software knows a lot about the data that it handles. We need 3 new CPU instructions for this design, and we have some secure memory as well. More detail on that later. So this is how we compute the integrity information. It's quite straightforward. We have a data block of 256 bits, and we compute this 56-bit MAC. And then of 32-bit chunks, we compute parity bits. And this is now 64 bits large, so it fits into off-the-shelf DDR5 ECC memory. The MAC computation is an important part because this has to be really quick. Because we have to compute the MAC on every read and write to the DRAM, and we don't want this to be slow. So we use the Karma block cipher. It's a block cipher developed by Qualcomm, and it's, for example, also used in ARM for pointer authentication. And we use this PMAC construction where we call a single Karma block cipher block 4 times in a pipelined mode, and then we get the MAC, and we can get the MAC in 5 nanoseconds. Compared to the 100 nanoseconds it takes to access the DRAM, this is not too bad. And I also have a performance evaluation later. So, okay, this is still straightforward, but now we want to correct bit flips. And the big problem is that MACs cannot correct bit flips. They're not designed for that. There's no linearity in there. That's actually by design. This shouldn't be possible. So the only thing we can do is brute force for the correct data. And we get some help from the parity bits there, which is actually great. So let's say we read data, the MACs do not match, but we see that in the parity bit, 1 bit is also wrong. So we know that the bit flip must be in here somewhere. When we look now at our correction hardware again, we don't have to, we know that the data here is flipped, and we know that the other data blocks are correct because the parity bits were all correct. So we can actually store these results from the Karma block computations from these data blocks, and only have to compute 2. We only have to run the Karma block cipher twice per try. And so overall, we can correct a single bit flip in 11 nanoseconds. If the bit flip is over here, we can even store 3 comma block outputs. Then we are just a lot faster brute forcing. So we could brute force this in hardware in about 11 nanoseconds. There's an S missing here. Okay. Oftentimes we see more than one bit flip, especially with hardware on newer DRAM that's actually worse than older DRAM. So we have to do something else. And this is where the software comes in. We have a new exception. It's quite similar to a page fault. It contains the physical address of the affected location. We need the physical address because if we would get the virtual address, we would need page tables, and page tables could also be faulty. So by getting the physical access, we don't need any other data structures. And then the first thing we do is the correction as a search. That's basically the same we do in hardware. We just brute force all possible bit flips until the max match. And we want this to be as fast as possible, of course, and we also want it to be as small as possible because of the secure ROM later. And this is how we came up with this beautiful code. Because the fastest way to try all possible bit flips are nested for loops. There's nothing that's faster and space efficient. And what you also want to do is we want to check for different amounts of bit flips. So we want to check for 2-bit flips, then for 3-bit flips, and so on. And we could either have different loops with different nestings, or we have this single loop here. And then it looks like this. This is quite straightforward. We have a flip mask, and then we XOR the data with this flip mask. We compare the max, and we XOR the bit back. So we try all the flips. And then we have this go-to labels here. Who doesn't love go-to? It's amazing. And now if we want to check for 2-bit flips, the code jumps to this label 2 flip. It tries 2-bit flips, and then it jumps out at the go-to at the bottom here. And if it wants to continue the 1-bit flip, the go-to label here is just set to the label just below it. And this is how we can flip multiple bits, try multiple numbers of bit flips with this long nested for loop. And all of this is possible because of a GCC extension, which actually allows you to get the address of a label with this double AND, which is not standard C, but because Linux is compiled with GCC, I guess we are fine. If someone wants to look at this code, here's the QR code. Please don't. Okay, how fast is this? This is actually not that bad. So here you can see we can do a single bit flip, of course, in the 11 nanoseconds we talked about. And then we go to the software. So first we have an overhead from the exception handler. This is why 2 and 3 bit flips take around 100 microseconds. And then the time increases exponentially, of course, but we still can do 5 bit flips in under a second, 7 bit flips in a few minutes, and 8 bit flips in almost reasonable few hours, 5.5 hours. If the data is really important, maybe that's worth it. And on the left, you can also see the times ECC takes. These are just numbers gathered from different papers that looked at ECC. So we are, for the hardware single bit correction, we are in the range of ECC. But brute force cannot be everything. We can do a lot more because software can be smarter. And this is where the advanced correction comes in. For example, a lot of data in the DRAM is actually also on the disk. All your application binaries, all your shared libraries, all the other memory mapped files that you have mapped. The page cache, for example, if there's a flip in the page cache, we don't even have to reload it. We can just remove it from the cache. So for all this stuff, we can just reload the data. We don't have to correct anything because we know there is a correct copy on the disk. Also for the kernel itself, that's a bit more complicated. The kernel would have to decompress itself again and maybe patch the broken part, but it could be possible. So no correction needed there. Another thing is that attackers, Rowhammer attackers, absolutely love tables. Not these kind of tables, maybe, but page tables. The data structures that map virtual memory to physical memory. Because the first privilege escalation attack actually shown, and which is still used in modern papers, attacks the page tables. So the page tables are data structures here in green that map this virtual page to this physical page. and there are many page tables per process. And if now an attacker hammers a page table and is able to change where this page table is pointing, with some luck, he can get write access to his own page table. And this means that the process can now map every physical memory in its own virtual memory. So it can access the kernel and every data of every process there is in the memory by just modifying its own page table. This is a pretty powerful attack primitive because it gives you access to everything. So we also checked in another paper how page tables actually look like in a system. And if you want to correct them, this helps a lot because we see that over 20% of the page frame numbers in the page table, this is the part that usually is flipped during an attack, is contiguous. So if we see that one page table entry is faulty, we can just look at the prior and next page frame number and then just use the one that's in the middle. And if the max match, we know that we have the same, the correct data again. So we know we don't need any brute forcing there. Or most of the page frame numbers in the page table are actually 0. So if we see a page frame number where everything is 0 except 1 bit, we know that it should be 0. So we flip this 1 bit back to 0 and the max match again and we are happy. So we don't need any brute force there. And this is true for many other data in the kernel where the kernel just knows how data structures look like. Maybe there are some bits that always have to be 0 and stuff like that. So brute forcing is really the last resort. We can do a lot more because we know stuff about the data we try to correct. There's one problem though, and this is that the max can also flip because the max is stored in the DRAM. And of course, if Rowhammer attacker can flip bits in the data, it can also flip bits in the MAC. And then if we would brute force data, we would brute force forever because we will never find the data where the max actually MAC if one bit in the MAC is different. And to solve this problem, we don't check for equality, but for approximate equality. I have an example here. So we compute them, we read data, we compute the MAC, we get this MAC, and then we get the MAC from the DRAM. And of course, they should match if the data is equal, but they don't because one bit is different. And now there are two possibilities. Either a bit in the MAC changed or a bit in the data changed and produced almost exactly the same MAC except for one bit. The second chance is really unlikely. So the chance that just a bit in the MAC flipped is a lot higher. And we can also do the math there. So we let this slip. We say, okay, they're almost equal. That's fine. We can do the math. I don't want to bore you too much with that. We have a 56-bit MAC here, and we now allow 3 bits to be different. And this reduces the MAC strength by actually a lot, from 56 bits to 41.2 bits. But this is still enough if we don't check for too many bit flips in the data. So we have a silent data corruption rate of 1 per 10 to the power of 9 billion years based on just random bit flips in data centers. And even with a very fortunate Rowhammer attacker that is able to flip multiple bits every 128 milliseconds for a full year straight, the chance of the Rowhammer attacker to find a second pre-image is still pretty low with 10 to the power of minus 4%. And this means that the attacker gets any pre-image that fits the max, but this is probably not data useful for an attack. So this approximate equality is secure enough for this threat model. Some minor notes, we have 3 new CPU instructions that we need. There's the CSI MAC instruction that just computes the MAC, because during the brute force in software and also during the other correction attempts, we of course have then to compute the MAC and check if it is actually correct. The CSI load instruction that loads data based on the physical address and doesn't throw an exception for corrupted data. So this is what we use to load corrupted data. And then CSI exchange instruction. That's not a simple write, just to curb some possible race conditions if, for example, multiple processes are correcting the same shared memory or something like that, because you don't have a simple write. That's also fine. So this is the basic design. It works pretty well. A remaining problem is that the operating system is software. Software is in the DRAM, so of course a skilled attacker could try to attack the exception handler or this correction as a search theme. So it attacks here. This is bad. And because of that, we put the exception handler and the correction as a search in a secure memory. We introduce this one. It's on the CPU, just like CPU caches, and it's only 4 pages large, so 16 kilobytes. This is tiny compared to modern caches, so not the huge area overhead there. And there we put the interrupt descriptor table, the global descriptor table. These are just what the CPU needs to run, basically, and then the exception handler and the correction as a search code. So only with those four pages, the CPU can execute this brute force attempt if the whole other system is broken, basically, and then try to correct the data. So, of course, we ran a performance evaluation. We implemented the whole system in Gen 5, which is a system emulator in C++. It simulates the whole x86 CPU. You can also run the Linux kernel in there. So we ran the Linux kernel on a system that is not under attack, so we only get the performance overhead from the MAC that is written and read, from the MAC that is computed on every read and write. And we ran many different benchmarks. The numbers are quite small, but you can see that the average performance overhead is less than 1%, and the worst overhead is a bit over 4%, which is also quite close to when we say we need 5 nanoseconds to compute the MAC, and we have on average 100 nanoseconds to communicate with the DRAM, you get like 4% performance overhead for a program that uses the DRAM a lot. So performance is good. Maybe some of you thought about this already in a bit more detail. There's one problem left in the advanced correction. Let's look at that. Let's say a corruption exception is coming in, and the exception handler always first does the advanced correction because it checks, okay, is this page maybe disk backed? Because then I can reload it from disk. I don't have to do a brute force search. The operating system does everything to not have to do a brute force search. So it always goes to the advanced correction first. Is this page disk backed? Is it maybe a page table? Is it a task struct, for example? There are also no more structure than for pure brute force. And then in the advanced correction, if it cannot do anything else, it calls this correction as a search handler. But now let's say exception is coming in. We go into the advanced correction handler, and the advanced correction handler sees, oh, this page is disk backed. Wonderful. So I just have to go to the disk and reload the data. I don't have to do a real correction. It goes to the disk through the ext4 driver, for example, and then there's another bitflip in the ext4 driver, or 2 bitflips. And now the advanced correction, or like the kernel itself, causes another corruption exception. It goes again in the exception handler, and the exception handler is like, okay, I first have to try, of course, the advanced correction to see what's going on. It now says, oh, this is a kernel page because it's in the ext4 driver. Kernel page is nice because I can reload it from disk. So it again takes the ext4 driver to get the kernel image, but again, of course, there's a fault in there. So now we have an infinite loop of exceptions that we cannot get out of, except if we detect this nesting. And if we enter the exception handler twice in the same process, we know that we can only do a correction as a search to be secure. And this correction as a search can now, with brute force, if it's just 2 or 3 bitflips, that's not too bad, first fix the ext4 driver, exits the nested exception handler, the ext4 driver is working again because it's corrected, and the ext4 driver can then not correct the bitflip, but just reload the disk, and the system is running again. And this is actually quite simple. In the exception handler, we just check if a nested bit is set. If it is, we do the error correction as a search. If it is not, we set the bit and do the advanced error correction, and at the end clear it again. And for the nesting bit, we have 2 requirements. The first one is that it is that it must be per process, because we allow multiple processes to run in the system, of course, and also we allow processes to run while another correction is going on. Because, for example, for disk accesses, this is interrupt driven, so the operating system is allowed to schedule another process. And if one correction is going on at the moment, and then another process gets an exception as well, this is not nesting because it's two different processes. It must be in the same process, so we need a nesting bit per process. And we want it in a register in time of the exception. Because if in the exception handler we have to check the DRAM to know if we are nesting, we don't want to access the DRAM because there can bitflips in there all the time. And on x86 there is exactly one possible register that fulfills two requirements, and that's the CR3 register. That's unique per process, and that's always in a register that's always loaded when the process is running, and it has a lot of higher bits that are unused. So usually it is made to contain the most top-level page table and PCID in the lower 12 bits if someone uses that. And in the higher bits, it doesn't use those, so we can use this for a nesting bit. And then we have this always in a register and always per process. But we could do even more. We had a great keynote talk today that AI can do everything now. So why not use AI for correction? And I tried that, and I asked ChatGPT if he can find the error in test message. You maybe found it already. So that it produces the following hash. The answer was actually quite reasonable. ChatGPT explained to me that SHA-512 hash function is a one-way function, and therefore this is actually not possible. Which is right, except if you try to brute force it, but this is apparently not allowed. But there are also smarter things we could try. For example, hardware acceleration. We already talked about this for a single bit flip. And then from a single bit flip, we go into software. And we could go back into hardware. If we look at the quite large CPU, Ice Lake SB Xeon server, it has a huge die. And this die would fit roughly 500,000 karma blocks. If one would build special silicon just for this correction method with 500,000 karma blocks, this could reduce the correction time for 8 bit flips from the half and the 5.5 hours we have in software to around 40 milliseconds purely in hardware. But of course, we do not want to have such a big die in every CPU. I mean, that doesn't even fit, or on every main board. But if one thinks about data centers, 8-bit flips do not happen often. This is a really, really unlikely event. So a huge data center could have one correction node that has maybe one or two of these, and then a computer which is not able to correct the bit flips itself through brute force can just talk with this node, hey, please can you correct this data for me? And it can send the corrected data back. So by going into software for the correction, there's just so much we can do. In the paper, we talk about a lot more, which I cannot talk now about because of time. We fully support virtual machines with this design, even if the guest does not support it. So there are two options. If the guest does not support CSI Rowhammer, the virtual machine host can try the correction as a search and also some advanced correction mechanisms. If the guest does support CSI Rowhammer, if one day this would become part of a CPU and part of the Linux kernel, it would just take some time for every Linux kernel also guest to support this. And then the guest can actually itself correct data with any advanced correction schemes. For example, reloading data from disk. CSI Rowhammer, of course, fully supports memory encryption, because this is used a lot nowadays. We also support not only the hardware correction of single bit flips, but also of stuck bits. This is actually a concern for huge server farms. If just a single bit or just a single connector of a DIMM, they can be faulty at times, and we can still correct these even faster because there we have more information about what's going on. And there are also some possible race conditions. Like I said, multiple processors can correct data and stuff like that. Race conditions can come up, but they don't bother us. And now I want to go back to the beginning, because I kind of made a promise here that with CSI Rowhammer, we don't care where the flips are coming from. The design is generic enough. So if some new attack would come up in the future, that's maybe not even Rowhammer, that's something completely else, or also if the bitflips come from cosmic rays or whatever, the CSI Rowhammer would still be able to detect that and act on it, correct the data. And sadly, the movie is not playing, but it's on my laptop playing. Okay. This laptop was just crashed by a press, and there's actually a new attack. It was, I think a year ago, it was published RowPress. It's quite similar to Rowhammer, but it is not Rowhammer. I will give a short introduction. The code looks similar. Here we again have multiple aggressor accessors, but all these aggressors point actually to different data in the same row. So all this program does, it accesses this row over and over again. 16 times, something like that, is what they found is the best number for most DRAM. It flushes the data again from the cache, and it accesses this row again. And after some time, if you do this often enough, bits start to flip again. And this is not Rowhammer. We know this for a few clues. One is that I said at the beginning, we have vulnerable cells, and if we hammer a row, the same victim vulnerable cells will flip again. For RowPress, we have different vulnerable cells. So it's not the same bits flipping if we Rowhammer or RowPress the same victim row. So this is a good clue that this is actually a different physical phenomenon that's going on. But it still flips bits from software. And of course, because this is so different, we only access a single row, and we don't try to have it like open and close as fast as possible, 2 rows. We access this 1 row and try to have it open as long as possible. This defeats many mitigations, because mitigations try to detect if multiple rows are accessed and stuff like that. But it would still be detected by CSI Rowhammer, because we don't care where the bit flips are coming from. We see data is flipped, the max do not match, and now we have to correct the data. So one could also call it CSI RowPress. Thank you very much.
Thanks, Jonas. We have some time for questions, if we have some. Do we have questions in the audience? Yes, we do.
Hello, thank you for the presentation. It was really good. With the predictable bits, do you think that they're related to the manufacturers? And would you be able to predict based on knowing their chipset which bits might then flip in future for future attacks?
The vulnerable cells are actually per chip, so they're due to fabrication differences. So I think there are works out there where you can fingerprint laptops or like computers through which bits are vulnerable to DRAM.
That's cool. Thank you.
Do we have any other questions? All right.
Sorry for my question, but in Rowhammer or RowPress, do you control a direction of the switch? Can you control like likely 1 to 0, or there is a way to switch from 0 to 1?
No, the thing is that I think with Rowhammer, bits always flip. So you have this capacitor and a transistor per cell, and Rowhammer always discharges this capacitor. But we see flips from 0 to 1 and 1 to 0 in a DRAM, and this is because DRAM manufacturers actually put some XOR mask over the data. So if you only write zeros, you actually write half the cells to 1 and the other half to 0. Probably some balancing. So this is why we see bit flips in both directions. But if a single cell is vulnerable, it always flips in the same direction.
My question is about introducing time variations. So let's assume with Rowhammer I switch a bit and I know the direction of it.
Mm-hmm.
And then with your error correction code, you introduce a time difference. So can an attacker, by observing time differences, deduce the harming weight of one part or deduce some information of the harming weight of the data?
That's a great idea. This work actually already exists. It's called RAM bleed. And you can also do this with ECC, because there you also have timing differences, and there is also some relation between the data in your aggressor rows and the data in your victim rows. And with RAM bleeds, by changing the data in the aggressor rows and then checking if bits flipped, they were able to deduce which data was in the victim row. And then they were able to steal cryptographic keys, for example. So we do not protect against that.
All right. Do we have any one question? Last question. Last call? No. All right. Let's give a warm round of applause to Jonas.